Greetings. My presentation today is a discussion of the MOTAS-NAT data reduction pipeline and the MG project status. I am Brian Craine, and first I would like to acknowledge some of my collaborators, Eric Craine, Roger Culver, Reagan Anderson, and especially Roy Tucker. Roy was the heart of this project, having designed and built the MOTAS system seen on the screen. His skills, curiosity, and imagination have been an inspiration to all of us. Unfortunately, Roy passed away this spring, and he will be greatly missed. The MOTAS system that Roy built is a scanning time delay integration system imaging a 48 arc-minute declination and was originally designed for asteroid discovery. Roy used the system very successfully, discovering over 700 asteroids in the early 2000s, but became less competitive when larger, well-funded surveys came on the scene. The MOTAS-NAT collaboration has repurposed the data stream as a series of surveys, primarily for the discovery of variable stars. The surveys are distinguished by their declinations, with each survey having a duration of about 2 years. MG7 was an experimental survey that included polarimetric imaging. MG6 is a repeat of the MG1 survey, providing a 10 to 12 year follow-up to the MG1 objects. The current MG8 survey is a repeat of the MG2 survey and will again provide about a 16 to 17 year follow-up of the MG2 objects. We are currently in the first year of the MG8 survey. The MG surveys accumulated imagery for an average of 270 nights per survey, varying primarily due to weather. They generated an average of about 84,000 images per survey. The initial reduction of the MG1 survey was done with a specific goal of producing a catalog of objects that were likely to be variable stars. The result was the MG1 VSC catalog, or Variable Star Candidate Catalog. It contained 26,402 objects that were high probability variable stars. The goal of this current effort is somewhat different. Namely, we want to develop a relational database of all the objects and their light curves within each survey strip. These master databases can then be used to generate subcatalogs, such as the original VSC catalog, or catalogs of even narrower definitions, such as long-period variables or non-periodic objects like quasars, through the application of data filters. To this end, we have developed a data pipeline to process surveys MG1 through MG6. These over 500,000 images presented a challenge to be processed by a typical home computer. To accomplish this task, we needed to balance the time required to develop the necessary software and the performance speed of the software. A C++ program could reduce the time to process the images, but would take a long time to develop. A Python program could be developed much faster due to an abundance of existing modules, but as a scripted language has a lower performance advantage. Balancing these factors, we decided to proceed with development of a Python-based data reduction pipeline and try to optimize the performance. Here are some of the key enabling modules we took advantage of. The AstroPy module provides a wealth of astronomical related functions, and we particularly use functions to handle FITS files and handle the world coordinate system conversions. EFIM is a convenient module for determining the solar angle at the time an image was acquired, allowing for automatic rejection of inappropriate images. NumPy is an essential module for scientific projects with Python, which facilitates array math and manipulation with great efficiency. PhotoUtils is a module that can be used in the detection of objects in the images and performing photometry. The one commercial package we used was Pinpoint, which includes an accessible dynamic link library, allowing for the plate solving locally. And finally, SQLite module provides functions necessary for the creation and handling of a relational database. The MG surveys are processed in two steps. The first is an image pre-processing step that prepares the images for photometry. This step is accomplished using our Python image reduction script. During this first step, we rely on AstroPy functions for performing the FITS file input and output operations. The right ascension of the center of the image is calculated, and AstroPy functions are used to then update that value in the FITS header. The actual image data is also exposed using AstroPy, which allows for reading the image directly into a NumPy array. Having accessed the image data, the utilization of the NumPy module becomes critical to the efficient processing of the data. The core of NumPy is well-optimized C code, which provides necessary and enabling processing speed, even though Python is a scripting language. Since our pipeline proceeds automatically, without supervision, it is important to be able to categorize each night's images as either overexposed, as dark field images, science images, and images to be used for flat fields. NumPy allows for the easy calculation of the mean pixel values of the images, which can be used as the basis for this categorization step. Overexposed images have a high mean value and are removed from further processing. The dark fields have a low mean value. The science images are between. The flat field images are chosen as the 10 lowest mean value of the science images, minimizing star density and the presence of very bright objects. Because the images are obtained in a scan time delay mode, the dark and flat fields can be prepared as a 1D array by determining a median row from either the dark frames or the flat frames. These are referred to as synthetic darks and flats. Again, this task is perfectly suited to a NumPy operation. During image acquisition, the scanning had been sequentially chopped into images by the process of reading the CCD camera. To ensure that data was not lost at this transition, portions of sequential images are digitally concatenated to provide an overlap with the next image. This is accomplished using NumPy for array manipulation. The one commercial package we use in the pipeline is Pinpoint. Pinpoint provides a Python-accessible dynamic link library, which allows for plate solving the images on a local computer, speeding up this process. Even with the local solution, this is one of the most time-consuming steps in the pipeline, typically requiring about 2 seconds per image, although some images may require up to 10 to 15 seconds. As a safety measure, we time out at 20 seconds. Images that don't plate solve can cause considerable time penalties. The second phase of processing involves the image photometry and cataloging of detected objects. This process starts with removing images obtained while the solar zenith angle was less than 108 degrees. The solar zenith angle is conveniently calculated using the EFIM Python module. We also remove images that had significantly uneven lighting, defined as having a quadrant with a median pixel value with a coefficient of variation greater than 0.05. These images are still available for possible use for follow-up studies of specific objects, for example, those that might be found in a good quadrant of the image. Photometry is performed on the remaining images and begins with a background subtract step. By way of illustration, we can see here an image with a problem region with considerable local unevenness in the background. A simple median background image subtraction does not work well in this situation, but has the advantage of being very fast. The Photutils Python package offers the source extractor 2D algorithm, which is very effective for background subtraction, even in this problem area. However, it imposes a significant time penalty, which was not practical. The use of a local median subtract using a sequential 32 by 32 pixel blocks resulted in comparable background subtraction to the source extractor, but at a much improved processing efficiency by nearly 50-fold. We therefore applied a local median subtract to all of the images. Object detection in these images was accomplished using the AstroPy DeoFind routine, which is a version of the DeoPhote routine from the IRAF software package. The object intensities were determined using the Photutils function for fixed aperture photometry. Minimum and maximum intensity thresholds were applied to help improve signal-to-noise ratio and to maximize linearity in the photometry. To assign a differential magnitude to the objects, we used an ensemble approach. We used 480 ensembles for each survey. The ensemble were all objects in a 3-minute span of right ascension, which matches with the original scan time of image acquisition. This resulted in different sized ensembles, with the smallest having 149 objects, the median number being 485, and the largest being 9,000, corresponding to the stellar density as a function of right ascension. This figure shows that the average magnitude standard deviation of objects in the different ensembles, in this case from the MG6 survey. It is apparent from that those ensembles that span the galactic plane around ensemble 380, where there is a large increase in number of stars per ensemble, also show a decrease in magnitude errors. This result can be more closely observed in the next slide. Here the standard deviation is plotted as a function of number of objects per ensemble. The greatest standard deviation in magnitude is clearly seen in ensembles with less than about 500 objects. In this reduction protocol, the error due to smaller ensembles seems to outweigh errors introduced due to stellar density. Differential magnitude is converted to an approximate apparent R magnitude. This is accomplished by using a published R filter magnitude for a fraction of the objects in each ensemble, generally about 60%, to define a second-degree polynomial fit with our determined differential magnitudes. This fit is then applied to all of the objects in the ensemble. This process is repeated for each observing season. Shown here is the result for 3 representative ensembles. We note that since we do not correct for color and other systematic differences, we can only expect an approximation of the R magnitude and only use this magnitude as a rough guidance for planning follow-up studies. In this slide, we see a comparison of the apparent R magnitudes for all of the objects between the MG1 survey and the MG6 survey, obtained 10 to 12 years later. The 2 surveys matched quite well using this methodology. The final step in the reduction process is to create a relational database to facilitate data handling and analysis. We use the SQLite module to create a simple database consisting of two tables. The Objects table contains an entry for each object found in the survey. The Measures table contains an entry for each photometric measurement and linked to the object from which the measurement was obtained. The Objects table also contains derived metrics unique to each object. This table can be expanded to include fields from other existing databases, such as parallax or color information from the Gaia database. Of course, the database can be searched and analyzed using structured query language, or SQL statements. We have now reduced all of the completed surveys, MG1 through MG6, and this slide shows a summary of those reductions. The number of nights of observations and the total images collected are shown by survey. The impact of bad weather during the MG3 survey period is evident. Since the MOTES system has multiple telescopes, there are two types of observations: those with one measurement and those that have a pair of measurements, that is, one from each telescope. The paired objects offer a quality check by requiring a minimum magnitude difference. The measurement rejection rate due to magnitude divergence is listed in the table as the paired reject percentage. This was an average of about 10%. The last two surveys had better performance of around 6.5%. There was considerable recovery of objects from the General Catalog of Variable Stars and the 2-mass catalog. We are particularly looking forward to the completion of the current MG8 survey, which will provide another long-term follow-up set of observations, giving a 16 to 17-year follow-up look at the MG2 declination strip. The survey databases are really just a starting point, providing a resource to point to follow-up projects. Some of the projects the NAT team are working on include discovery and characterization of M-dwarf eclipsing binary stars. At least 6 new examples have been discovered and characterized. We're also characterizing long-period variables, combining the MG1 and MG6 data has more than doubled the number of long-period variables found in the original MG variable star catalog. The MG surveys provide a resource for analyzing long-term light curves on time scales of 10 to 15 years. These curves may prove useful in the search for a periodic quasar. I will refer you to the presentation by Doug Walker at this symposium. The MG databases also provide a good resource for recovering pre-discovery supernova light curves. The MG survey points to a large number of short period variable stars which require follow-up observation to establish variability type and to pin down their period. Perhaps most fun of all is the analysis of odd, serendipitously discovered objects, which has, for example, led to the long-term monitoring of a periodic, chromospherically active star with surprisingly strong, energetic optical outbursts. NAT is searching for collaborators that can contribute to these follow-up projects or that can see a role for the MG surveys in other interesting projects. Collaborators who have access to spectroscopic systems that can achieve high signal-to-noise spectra to magnitude limits 14 to 17 are especially sought after. Thank you for your attention.